Okay, I think we can start with the presentation. Welcome all to this second joint math colloquium co-organized with Universidad Complutense, represented by Pier Giulio Tempesta, which is unfortunately lecturing at this moment. Universidad Autónoma, represented by José Conde, and CSIC, represented by José Ignacio Burgos Gil, and Carlos III, of course, which are the institutions supporting the ICMAT. And 1 year ago, I said long life to this colloquium, and well, we managed to make it live 2 years. And I hope it's going to be many more years. This seminar colloquium is going to be streamed so that other people from the different universities and now in the Congress at ICMAT are following, hopefully, the colloquium. I'm very pleased to introduce Briët, our speaker today. He's a researcher of the Algorithm and Complexity Group at CWI, which is the Research Institute for Math and Computer Science in Amsterdam, and he's also a member from many, many other research groups. For instance, the Dutch Research Center on Quantum Software and Technology with the poetic name of QSoft. So I'm saying this, I promised Job to not to blow up the presentation, but maybe later we have a coffee, and so you may want to ask him or speak to him. So let me just say that Job did his PhD in 2011 and took it from the University van Amsterdam in computer science. But well, Job has many other interests, and he has articles in functional analysis, number theories, one of those scientists looking at other fields, which is something I sympathize very much with. He has been visiting also several years the Quran Institute in New York. He's editor of Theory of Computing, which is an open source journal, which you may also ask him after in the coffee. It's a very nice initiative. And as I told you, he has many, many interests, and today we will show this manifold of interests, and his talk today will be randomness and structure and combinatorics, analysis and computer science. And please, if you want to intervene, interrupt, it's a colloquium, but you can do it anytime. The only thing, you have to call me because we need for the people on the other side to pass the microphone. But even with a microphone, just be free to ask questions anytime. Thank you very much, Job. Thank you for coming here and giving this talk.
General questions. What does it mean for an object to be like a random object? How can randomness be measured? And what properties might you expect from objects that deviate from typical random objects? So like I said, these are extremely general questions, and there are many, many possible and known answers to these questions. The nature of these answers depend very much on the setting you're interested in and what you might like to do with these answers. Okay. So there's way more answers than I could possibly cover today, possibly also in a week. So I've made a small selection of topics that pertain to these questions. If you have any questions of yourself, please ask me and interrupt at any time, of course. So the first thing I'd like to start with discussing comes from combinatorics. So these questions have very beautiful answers in graph theory. So just to make sure that we're on the same page, this is a graph. The black dots are vertices, the black lines are edges. Okay, so I'll be dealing with finite, mostly simple graphs. A subgraph is just the graph you see when you only focus in on a few selected vertices. Okay, so perhaps before I start talking about what a random-like graph is, we should agree on some model for a truly random graph. And perhaps the most studied model is the so-called Erdős-Renyi random graph, GN1/2. N stands for the number of vertices, so you start with an empty graph with n vertices, and then afterwards you include every possible edge there is and choose two edges independently from the others with probability 1/2. This gives you a random graph, and what's been studied are many, many nice aspects, and I'll just focus on a few of these things. So this is a very powerful model to study networks from a very large variety of perspectives. Okay, so what's typical is to study this model in a setting where n is finite but tends to infinity, and you ask for asymptotic behavior as this parameter n, the number of vertices, grow. So there's a number of things you can typically expect from an Erdős-Renyi random graph. The first thing has to do with the number of copies you can expect it to be of an S vertex graph H. So S is some arbitrary number that is of your choice, but is supposed to be independent of the number of vertices n. So with very high probability, the number of copies of any S vertex graph A, H is what you would expect. So if you compute the average number of copies, this is what this number here is what you would work out to. Okay, so an S vertex graph has S choose two possible edges. So this includes edges that you include and edges that you don't include. So you would expect the probability of a single copy of H on a particular subset of S vertices from your Erdős-Renyi random graph to be 1 over 2 to the S choose 2. And then there's n to the S roughly possible S tuples you can choose in your Erdős-Renyi random graphs. Okay, so you might expect an n choose S here, but this concerns labeled copies. Okay, so you can choose which vertex means which in the graph. So it turns out that the typical number of copies is extremely close to what you would expect. Okay. A second property has to do with the edge distribution, something called uniformity. If you take two large vertex subsets in your Erdős-Renyi random graphs, subset S and subset T, the number of possible edges between them is just the product of their sizes. Okay? Each edge is picked independently of the others with probability at 1/2. So the expected number of edges that are induced by two, say, disjoint vertex subsets S and T is their sizes, the product of their sizes divided by 2. And it turns out that the actual number of edges between any pair of vertex subsets of your choosing will never deviate, or with high probability not deviate by too much from this expectation. Okay, so this will be little o of 1 once you divide by 1 over n squared. 1 over n squared is roughly the maximum number of edges you can induce by any pair of vertex subsets. So, in colloquial terms, an Erdős-Renyi graph is typically uniform. There's a third property that's somewhat more linear algebraic that concerns the adjacency matrix of the graph. So the adjacency matrix has its rows and columns indexed by the vertices of the graph. It has a 0 if the edges corresponding to the particular row and vertex you're looking at is 0, and it has a 1 if the edge is present. Okay, so the adjacency matrix of a random graph is a random matrix. It's symmetric, and so it has eigenvalues, and you can arrange the eigenvalues in decreasing order. So say lambda 1 is the largest eigenvalue in absolute value of this matrix, lambda 2 is the largest in absolute value after the first one, and so on. And it turns out that with very high probability, an Erdős-Renyi random graph will have the property that its second largest eigenvalue in absolute value is little o of n, much, much smaller than the first eigenvalue. This first eigenvalue will be approximately n over 2. So if you divide by that, you typically expect the second largest eigenvalue in absolute value to be asymptotically smaller than that. Okay? In colloquial terms, an Erdős-Renyi graph is a spectral expander. Okay? So these are typical properties, 3, of a truly random object. Okay? And so we might agree that a fixed object that you're looking at, or maybe a family of graphs in which the number of vertices goes off to infinity, looks like an Erdős-Renyi graph if it shares with it one of these typical properties. You might ask, okay, which one should I choose? And there's a beautiful result from the late 80s by Chung, Graham, and Wilson that says that it doesn't matter which property you choose. So what they proved is that for any n-vertex graph, or you should really view this as a result about families, where n goes off to infinity, whose edge density is a half, so that's the expected edge density of the Erdős-Renyi random graph. If it satisfies any of 7 typical properties of the Erdős-Renyi random graph, so I showed you 3 of these 7, they found 4 more, then it necessarily satisfies all of them. There's no way to just satisfy one of them. And so one could say that a graph is random-like, or they say quasi-random, if it shares any one of these properties. Okay, and it doesn't matter which one you choose. Beautiful result. So you might wonder, well, are there any such fixed graph? I know the probabilistic method, the Erdős-Renyi graph, typically gives me one, but show me an actual example. So here's a picture of one. The family of Paley graphs, or quadratic residue graphs, so indexed by the elements of a finite field of prime size, where the edges are formed by pairs whose difference is a square, has density a half, and it's quasi-random. So it's not so difficult to show using basic Gauss sums from analytic number theory that this graph is a spectral expander, and by the theorem of Chung, Graham, and Wilson, it means that it automatically also satisfies all the properties you would typically expect from an Erdős-Renyi random graph. Okay, so this is actually a specific instance of a somewhat more general result. For concreteness, I chose to include the edges with probability a half. The same thing holds if you replace this 1/2 with a fixed parameter somewhere between 0 and 1 that's independent of n. And in that setting, what you're talking about are dense graphs. So graphs that include a positive proportion of all possible edges. But it's also interesting to study quasi-randomness for sparse graphs, graphs that have significantly fewer than all possible n squared or n choose 2 edges. So an n-vertex graph is sparse if it contains little o of n squared edges. So here is gn with some other parameter. So this other parameter, so this is again an n-vertex graph, and this parameter tells you the probability with which you sample each edge independently of the other. It turns out that if you sample the edges with probability log n over n, in which case any single vertex will typically have not n, but approximately log n neighbors, very few neighbors. This is an extremely sparse graph typically. It will still be a spectral expander. Okay, so this deviates from the perspective of Chung, Graham, and Wilson in that it concerns very sparse graphs. It turns out that the same holds in a slightly different model. So here edges are picked independently of each other. You can also pick uniformly from the set of graphs in which every vertex has exactly 3 neighbors, the 3 regular graphs. When you do so, you get a sparser graph than you would typically get in this case. So in this case, every vertex has only 3 neighbors. In the Erdős-Renyi setting, a typical vertex has approximately log n vertices. A uniformly random 3 regular graph also turns out to be a spectral expander with high probability. The question.
Can you repeat again, please, what a random 3 regular graph is? I didn't
quite
get it.
Yeah, a graph is 3 regular if every vertex has exactly 3 neighbors. Okay, and so you can take your collection of 3 random graphs and take the uniform distribution over all 3. That's a random 3-way group. Yeah. Okay, so this is an extremely sparse set of graphs, but they have this property you can typically expect, right? It's a spectral expansion, very small second eigenvalue. So these are called, colloquially, expander graphs. Expander graphs are sparse graphs that are spectral expanders. These things have extremely nice properties. For example, they're extremely well connected. So you might, if you're constructing, say, an electric network, apparently this is a model of the power grid in Europe, expansion is an extremely nice property because spectral expansion implies high connectivity. It's just to connect 2 very large set of nodes, you would have to cut many, many edges. So a spectral expander gives you an extremely robust network. At the same time, connections cost money if you're installing a power grid, so you would like this thing to be sparse. Okay? So sparse expander graphs are extremely useful in practice. If you're into social media and you want to spread gossip, expander graphs are also very nice. If you have some juicy piece of news and your social network happens to be a very sparse expander, meaning that everyone is somewhat antisocial, has very few friends, you can still spread your rumor extremely quickly by just telling all of your neighbors and telling them to tell all their neighbors again and again and again. Typically, it will take only log of the size of the network's number of steps before everyone knows your piece of good, juicy news. There's different perspectives on them. They're rapidly mixing. If you start with an arbitrary node in your network and then do a random walk, so you pick, at every step, you pick a random neighbor to move from within roughly a logarithmic number of steps, your distribution will be approximately uniform over all of the vertices. And this is extremely useful in theoretical computer science, where randomness is potentially, seemingly an extremely useful resource when it comes to the design of algorithms, but it's also very hard to come by in practice. And the fact that random walks are very rapidly mixing implies that you can sometimes reduce the amount of randomness you need to construct good algorithms in theoretical computer science. So these are some reasons why spectral expanders or expander graphs are quite useful. Good, so I started talking about equivalent notions of expansion for dense graphs. It's a theorem of Chung, Graham, and Wilson. So a natural question to ask is if spectral expansion implies uniformity for sparse graphs also. Recall that uniformity had to do with the idea that you select 2 large vertex subsets, and it had something to do with the number of edges you induce between them. Okay? You want this to be roughly what you would expect in the random model. And so about 20 years ago, Chung and Graham asked, does this equivalence that was shown in their joint work with Wilson also hold for sparse graphs between these 2 notions? In one direction, it does. So there's a thing called the expander mixing lemma, which shows that so lambda is the second largest eigenvalue in absolute value, and U stands for the uniformity. Okay. Turns out that spectral expansion implies uniformity for any graph. This is a basic linear algebraic exercise done by many people in computer science and combinatorics. There's some bad examples that show you that you can't go the other direction in general, however. There are uniform graphs that are not spectral expanders, unfortunately. So this seems like these nice equivalents break down in general. But there's a very nice result that shows that symmetry saves the day. If you restrict your attention to so-called Cayley graphs, the Paley graph, of which I showed a picture earlier as an example of this, there this equivalence is intact still. Okay? And it turns out that something more general is true for a larger class of graphs, and this brings me momentarily to an interlude from functional analysis to functional analysis. So to generalize this result, it turns out there's an extremely useful result from the 50s proved by Grothendieck in the context of the geometry of the tensor products of Banach spaces. Yeah.
By Cayley graphs, you mean the graph of a finitely generated group, the usual?
Yeah.
So they are kind of special.
They are special, yeah. They have a high degree of symmetry. and it turns out that symmetry is exactly what you need if you want this equivalence between spectral expansion and uniformity.
Okay, thanks.
Yeah. Okay, so a little bit about the tool from functional analysis that allows you to generalize this result. This tool is Grothendieck's inequality. Okay, so I dumped a huge equation here, and let me take a few moments to try and roughly describe what it says. So there's a given matrix of size n by n and an integer d, okay? And associated to this, I'm defining a number, SDP sub d of a. So it's a supremum over functions, f and g, on the set of integers into the d minus 1 dimensional Euclidean unit sphere, okay? Okay, so the way to maybe picture this is that you have a system of 2n particles, and each particle has associated with it a spin, which is represented by a d minus 1 dimensional Euclidean units vector. And what you're trying to optimize is a configuration of these spins. The matrix tells you how the spins are supposed to interact. So if the matrix has a positive entry, you'd like the spins to align. If it has a negative entry, you'd like them to anti-align. And this product tells you the extent to which the configuration of spins satisfies these constraints, okay? So this SDP sub d of a, in a sense, measures some kind of energy of the system that you'd like to maximize. Physicists like to put a minus sign, and then they're talking about ground state energies. I ignored the minus sign, and I'm maximizing energy here. So you can let d vary from 1, say, then physicists would call this the Ising model. If d is 2, it's the XY model, 3 is the Heisenberg model, but you can let d grow further, and then I don't know what the names are, okay? In general, the intuition you should have is that it's more difficult to satisfy the constraints of this matrix when d is small, okay? And so you could maybe imagine that the energy, the maximal possible energy, increases as d increases. Grothendieck tells you that there's a definite upper bound to the advantage you get from increasing d. So in the 50s, in a completely different language, Grothendieck showed that there's an absolute constant, now known as the Grothendieck constant, such that for any d of your choice, SDP d of a is bounded between SDP1, the XY model, the spin model, and this factor kg times SDP of 1. Increasing the dimension only buys you a constant factor advantage, okay? It's difficult to understate the ramifications of this result. It's relevant in statistical physics, combinatorial optimization, hence the notation SDP. It turns out that when you let d go to infinity, you can compute this number efficiently using semi-definite programming. When d is equal to 1, this is an NP-hard problem to compute, so it's relevant also in computational complexity. Turns out to be relevant in the study of quantum entanglement, special interactions between pairs of physical systems that you locally measure. Quantum algorithms, algorithms for community detections in large graphs or networks. Graph clustering algorithms are based on this inequality, and so-called regular decompositions of graphs that I'll say a little bit more on later. Major open problem is to determine exact value of the Grothendieck constant, okay? Grothendieck posed 6 problems in his 1950 works, 5 are solved. This is the one that's left open, okay? Despite its relevance and ramifications, we don't know the answer to this question. Okay, back to uniformity and spectral expansion. There is a nice work by Condon and Zhao from 2017 that shows that the ratio of the spectral expansion of a graph and its uniformity is at least 1. This is the expander mixing lemma that I showed earlier, and at most 4 times the Grothendieck constant. Okay, coincidence? It turns out not. What's more, with my colleagues Bonink, Labib, and Maassen, we showed that the use of Grothendieck's inequality in this result is essential. You can characterize the Grothendieck constant as the largest possible ratio of these 2 parameters. So Grothendieck's constant is relevant in quasi-randomness of graphs also. So that's kind of a detour via functional analysis, geometry of Banach spaces, although I didn't say much about that topic, but that's where this result came from. So here's a pro tip, which got me into this topic actually. If you see something about Grothendieck inequality and you have a new application, don't stop there. There's many generalizations of Grothendieck's inequality, that will probably allow you to, almost for free, get some new results in quantum information theory. Okay? So the result I flashed by Coleman and Zhao that shows that spectral expansion and uniformity are equivalent. Sorry, I forgot to mention this. For vertex transitive graphs, that's a generalization of Cayley graphs. So these are highly symmetric graphs. This saves the relation between uniformity and spectral expansion. So this is the general class for which uniformity and spectral expansion are equivalent, vertex transitive graphs. It turns out an analogous statement is true for quantum channels. So these are the most general operations one can do on the state of a quantum mechanical system that's allowed by nature. Turns out quantum channels, in a sense, generalize graphs. I won't go into why. Irreducibly covariant quantum channels turn out to generalize vertex transitive graphs. Spectral expansion turns out to be very relevant for quantum channels for a variety of reasons having to do with the use of randomness in quantum information theory. They allow you to, in a sense, replace a Haar uniform unitary matrix, which should be thought of as a uniform random variable, with a much simpler object. And there's a combinatorial notion related to uniformity also for quantum channels. And it turns out what's true for graphs is also true for quantum channels via the same reasoning, via a non-commutative version of the Grothendieck constant. Right, so quantum channels, quasi-random quantum channels, spectral quantum channels, what should I call them? Quantum expanders are useful in randomness reductions in quantum information theory, quantum cryptography, and the study of multipartite entanglement. Okay, so this was all about objects, graphs, channels that have some kind of randomness. You can also start with an arbitrary graph and ask if you can force some randomness out of it, and that turns out to be possible. There's a beautiful result by Szemerédi that tells you that given an arbitrary dense graph, you can decompose it into a constant number of pieces, all roughly of equal sizes, so that most of the pairs of these pieces interact in a random way. So there was no assumption made on the initial object, and the randomness between the pairs of pieces has something to do with the edge distribution of the bipartite graph induced by them. So there's a way in which you can decompose an arbitrary large object in pieces that interact quasi-randomness. So this is the picture you might have in mind. Here we have 5 big pieces that before formed some arbitrary dense graphs. When you glob them together, what you see in between them when you zoom out is something that, an edge distribution that looks pretty much uniform. Okay, so there's very few irregularities between these 2 big pieces. And perhaps, I think these are flights between various cities in the world. If you zoom out, then you can see clusters appear, and between them there's kind of shaded lines that don't display much variation whatsoever. Okay, and this so it turns out that Grothendieck's inequality is algorithmically useful. It allows you to find such decompositions efficiently and algorithmically. Is there a question? No. Okay. So yeah, there's a question.
Means independent of the number of vertices.
That's correct.
So T is fixed for any graph.
Yeah, so there's a constant, so this is kind of high level. You get to choose kind of a randomness constant, epsilon. That determines how many pieces you might need, and it governs the level of randomness you can expect from the interaction between most of the pieces.
Okay, and T is what, polynomial in epsilon, or so it has a...
I think it's horrible, like tower type. Yeah.
Okay.
I'm not sure if you can expect anything better, but it's constant once you've chosen epsilon. Yeah, but it's independent of the size of your network. That's the most important part. Okay, so this is all I wanted to say about graphs. This lemma kind of is a natural transition to a second setting in which you might want to study quasi-random objects, namely subsets of finite abelian groups. One of the reasons why Szemerédi proved this lemma is to prove a result in combinatorial number theory, reprove a result in combinatorial number theory proved by Roth in the 50s. So this is an application. I think I'm going a little bit slowly, so I'm going to skip an application, an algorithmic application that allows you to test large networks using the regularity lemma. Okay. So Roth's theorem, a theorem from combinatorial number theory, tells you that if I give you an arbitrary set of the first n integers, that's dense in the sense that it contains an epsilon fraction, n should again be considered a parameter that goes off to infinity, then there's no way to choose this set so as to avoid it containing three-term arithmetic progression. So a triple of the form x, xy, x plus 2y. Any dense set will always contain such an arithmetic pattern, provided n is large enough in terms of epsilon. Okay. So this was first progress towards a major, still open problem of Erdős. So Erdős conjectured something much stronger. What he conjectures that if you take a subset of the natural numbers, such that if you add the reciprocals of the elements in your sup and you get some in your set and get that it diverges, he conjectured that such a set must contain arbitrarily long arithmetic progressions. This problem is still wide open. Roth made a first step, but the content of this theorem is not enough to even make progress on the 3AP case of this conjecture. It's been solved in some cases. So if A is a set of primes, this is perhaps the most natural set satisfying this property. It's been confirmed. So the primes contain arbitrarily long progressions. This is a very famous result of Green and Tao, and it uses randomness properties of the primes. Okay, so maybe that's the first thing you might expect. Primes are see a cryptographer nodding, of course. So it heavily uses the fact that the primes, even though there's nothing random about them, have properties you would expect from random sequences. Okay, the 3AP case is solved, but it's not implied by Roth. It's implied by a strengthening of Roth's theorem that proves good bounds of the dependence of n on epsilon by Bloom and Cisask only a couple of years ago. And I'd be remiss not to mention the major breakthrough of Kelly and Mecca that again improved this result of Bloom and Cisask. Okay, I guess maybe I won't say much more about that. I just perhaps want to mention that this is a highly active area of research that is seeing major progress within the last month, actually. But further than that, Erdős's conjecture is wide open. What I want to focus on is Roth's strategy for proving his result. And it starts with the observation that if A is random and has density epsilon, then it actually contains many arithmetic progression. Why? If you select each element of the integers between 1 and n with probability epsilon, then any fixed three-term arithmetic progression is present with probability epsilon cubed, if you choose them independently, right? And so if you go over all possible three-term arithmetic progression, you find that there's approximately epsilon cubed times n squared arithmetic progression in a random set. So suppose you were to find a set that contained no three-term arithmetic progressions, then it had better not be randomly chosen. There must be something about this. And this is kind of the idea behind a proof strategy towards proving Roth's theorem. So back to Chung and Graham without Wilson this time, they proved a theorem similar to the one I flashed some time ago already, that tells you that if a set has size epsilon n, then there's 9 typical properties you can expect with high probability from a randomly chosen set that imply each other. Okay? So there's 9. I don't have enough space to list 9 of them, but I'll list 2. The first one tells you that for almost all elements y, the number of pairs in your set A that have the property that they form the first and last elements of a 3-term arithmetic progression in which y is the middle element is approximately what you would expect if A was randomly chosen. Okay? So x, y, and z form a 3-term arithmetic progression in this group if and only if they satisfy this equation. That's the point. Okay? The second has to do with it's a Fourier analytic type of property. If I look at the indicator of my set, so this is a function that takes value 1 if x is in your set and 0 otherwise, and you compute its Fourier coefficients, so this finite abelian group has its characters associated with it, so the homomorphisms from your group to the complex numbers with multiplication endowed with them. The Fourier coefficients of this indicator function, except for the trivial one, are all extremely small. So this Fourier spectrum of such a set is essentially flat. Okay? That's the second property. It turns out these are properties you would expect with high probability from a randomly chosen set, and they imply each other. So back to my observation. If I have a set that's quasi-random, or random, truly random, then I expect it to have many three-term arithmetic regressions. This result shows you that if it doesn't, then it cannot be Fourier uniform. Okay? So a lack of three-term arithmetic regressions means that this indicator function correlates, has large inner product with a non-trivial character. But differently, if my set is not random in the sense that it lacks arithmetic regressions, then it must be structured in the sense that it correlates with a structured function. I'm not going to go into the details, but it turns out you can use that to your advantage. If you contain no 3 APs, then you correlate with structure, and you can take the structure to your advantage to show that there is a long arithmetic progression on which the set has increased density. And this sets up an inductive proof, so you can then repeat the argument. Restricted to an arithmetic regression, you will still not contain three-term arithmetic regressions, and you can keep doing this, provided n was big enough to begin with. In the end, you'll end up with a set whose density is strictly larger than 1 and reach a contradiction. So that's, in a nutshell, how you can prove Roth's theorem using a structure-versus-randomness type of argument. Szemerédi generalized Roth's theorem to longer progressions. Okay. So this is Szemerédi's theorem. Any dense, roughly speaking, any dense set of the first n integers contains a k-term arithmetic progression, provided n is large enough in terms of epsilon and k. So Roth concerns the case k is equal to 3. So Szemerédi saw Roth's theorem and wanted to generalize it to longer progressions. The problem with Roth's proof was that he didn't know how to generalize this Fourier analytic argument, and so he reproved it using combinatorial argument, and key ingredient is his regularity lemma that I showed you earlier, the fact that you can decompose dense graph into quasi-random parts. Okay? But that gave terrible bounds. So this is the kind of proof that he could generalize to prove his k-term arithmetic progression version, but it gave terrible bounds. In a sense, it was much worse than Roth's strategy. So motivated by that, Gowers worked very hard and managed to reprove Szemerédi's theorem, but using Fourier analytic arguments. Again, using a structure and randomness type of argument. So the hope is that perhaps you can do something similar as we argued for Roth. If I take a random set of density epsilon, then it will contain approximately epsilon to the 4th fraction of all 4-term arithmetic regressions. Okay. So you might hope, well, if it doesn't contain any 4-term arithmetic regressions, perhaps it's not uniform and I can do the same thing as I proved for Roth. And it turns out that doesn't work. So Gowers has a counterexample of a set that's actually very dense. It's Fourier uniform, but it contains very few 4-term arithmetic regressions, many fewer than you would expect from a random set of the same density. So this shows that somehow Roth's strategy is not going to work in this case. Okay. There's a similar example, but over finite fields. So these theorems, they work fairly generally over finite abelian groups, and a model that's often used is a finite field setting where you replace the set of integers between 1 and n, or the integers modulo n, which are more or less equivalent, with a finite vector space. And there's an example somewhat similar to Gowers, where the set A is constructed to be the set of x that satisfy this nice quadratic equation using the Chevalier-Warning theorem from basic algebra. You can show that the set is dense. It contains about 1/5 of all the elements there are. But because of this equation, you can also show that if this set contains a 3-term arithmetic progression, it will necessarily contain the 4th point of the arithmetic progression when you continue it in the same direction. You can also show, using a Gauss sum again, that this thing is Fourier uniform. So the Fourier spectrum is essentially flat. That implies that it contains many 3-term arithmetic regressions, and so that by the second bullet, it contains many 4-term arithmetic regressions. In fact, many more than you would expect from a random set with the same density. So this is a second example that shows somehow that uniformity doesn't capture the fraction of 4-term arithmetic progressions very well. But there's something telling about this example, namely that there's a quadratic equation here. And that turns out to be essential also in this counterexample of Gowers. So Gowers came up with a different measure of quasi-randomness that was relevant for 4-term arithmetic progressions that replaces Fourier uniformity. So it's based on something called multiplicative derivatives. So given a function on the integers mod n to the complex numbers and some direction h, you define the multiplicative derivative of f in direction h at x as this product here. If f is some function in the exponent of an appropriate root of unity, what you see in this exponent is really the discrete derivative of your function. And the Gowers uniformity norms look at iterated derivatives of a given function. And then you take an expectation that's uniform over the point on which you evaluate this and the direction you take. And what this measures, what these norms, these really are norms for k at least 2, measure is the degree of oscillation of your function after you take a number of derivatives. Okay, so if you see no more oscillations whatsoever, if this norm is very big because there's no cancellations, you might expect that this function resembles a polynomial type object. And that turns out to be true. This norm is relevant because it allows you to estimate the number of 4-term arithmetic regressions when you set k is equal to 3. Turns out for an arbitrary set, the number of 4-term arithmetic regressions minus the number you would expect from a set with the same density is governed by the Gowers 3 uniformity norm of the indicator minus its density times the all ones function. Okay? So this is telling us that if a set contains very few or no 4-term arithmetic regressions, and this difference is very big, this function here, the balanced function of our set, has large U3 norm. Okay? So this should be compared with what we saw in Roth's theorem. If a set contains no APs, then it's not uniform, and so it correlates with structure, and that turns out to be to be true in this case as well, thanks to some very deep theorems of Green and Tau and Ziegler that tell you that if a function has a large uniformity norm, then it correlates with a highly structured object. In the case of, so G here, let's see, so G is, let's say, a finite abelian group. If it's the integer modulo n, then there's correlation with very difficult objects called k-1 step nil sequences. Here's an example of such a thing. When k is equal to 1, this is just a homomorphism. Okay? When k is 2, we see a quadratic thing appear, right? Which should be reminiscent of the counterexamples I showed. But this is just a tiny example of these nil sequences. These are much more complicated objects, but this is the intuition you should have. They are, in a sense, polynomials in phases. Over finite fields, they are exactly what you might expect. These structured objects are just polynomials raised to some appropriate root of unity. Okay, so non-uniformity implies correlation with structure in a polynomial sense. And using this, you can again fix the proof of Roth's theorem in a somewhat more general setting. A lack of randomness implies correlation with structure, and you can again use this in an inductive proof to prove Szemerédi's theorem for longer progressions. Okay, so I think I have about 5 minutes. I'm going a little bit more slowly, so I very quickly want to flash some of the things I've been working on in this context. So Szemerédi's theorem was reproved again by ergodic theorists, and this kind of opened the floodgates to a series of super powerful refinements of it concerning things called intersective sets. And intersective sets have to do with the common difference in arithmetic progression. So if I have an arithmetic progression x plus y, x plus 2y, Y is the common difference. Okay? So a set D is said to be 2 intersective if a dense set A contains a 3-term arithmetic progression with common difference in D. So Szemerédi's theorem tells you, or Roth's theorem tells you, that the integers themselves are 2 intersective, but there's, from ergodic theory, there's people who, Bergelsen and Leibniz, show that, for example, the perfect squares are also intersective, and also the shifted primes turn out to be intersective, and there's many more examples. So these definite results led to a line of questioning that asked about the special character of these examples. In particular, it's been asked, what can we expect from random sparse sets? So if D is a random set, is it typically intersective, or are these sets really privileged? So suppose you choose a set randomly from all sets of size m, and you let m increase. There turns out to be a beautiful phenomenon known as a threshold phenomenon that says that as you let the size of D increase, there is a point, m star, at which the probability that this set is 2 intersective jumps from nearly 0 very quickly to 1. So there's a spike. And a big open problem in this area is to determine this value of m star. So just not so long ago, using some ideas from theoretical computer science from a breakthrough from last summer, my postdoc Davi Castro Silva and I proved the best upper bounds n to the 1/3. But these are very, very far away still from the conjectured upper bounds, or the conjectured correct bound is log n. Okay, so we're extremely far away from this. The reason why I mentioned this is that this conjecture has to do with the structured object I talked about a slide ago. So the conjecture concerns so-called functions called 3 AP dual functions. They look like this. What they allow you to do is count the number of 3-term arithmetic progressions with a given step D. So you can let F, G, and H here be the indicator of the same set, and this counts the fraction of 3-term arithmetic progression in a particular direction of your set. There was a conjecture or an expectation from the field that these functions are highly structured in the sense that you can decompose them very well in terms of quadratic phase functions. So these two-step nil sequences I flashed before, in case G is the integers modulo n. Not unlike, it's kind of vaguely reminiscent of the way that Szemerédi decomposes an arbitrary graph into quasi-random objects. This turns out to be false, however. So a couple of years ago, with Green, I showed that the expectation that you can well approximate these 3 AP dual functions using these quadratic-like object, two-step nil sequences, that turns out to be false. So that puts this conjecture of log n on a little bit of shaky ground. Okay. Okay. So this is perhaps the last thing I want to mention concerning details. I just wanted to flash a few other areas that I definitely don't have time to talk about that are somehow related to these notions of quasi-randomness, in particular in the second half of my talk. So the study of functions in terms of these kind of polynomial type objects, polynomial phase functions, is nowadays referred to as higher order Fourier analysis, kind of still developing field, and ideas from that turn out to have applications in a wide variety of other areas. So you can use ideas from this to come up with very fast testing algorithms for error correcting codes. They also allow for the development of tests for quantum entanglement in non-commutative settings. These ideas have been lifted to non-commutative settings. I've used them to prove counterexamples to hoped for generalizations of the Grothendieck inequality from functional analysis. They allow you to study the structure of quantum Fourier algorithms in terms of polynomials. They turn out to be related to questions concerning the computational hardness of efficiently decoding error-correcting codes. And a thing that I'm currently working on has to do with local tests for quantum measurements, so general properties of quantum mechanical devices that you can infer by just making simple measurements in non-commutative settings. So this would have to this has to do with trying to generalize these Gowers inverse theorem to tell you if a function have a large Gowers norm that it correlates with structure, to non-commutative settings, where you study functions over arbitrary groups that take values in matrices. Okay, so I think my time is up, and that's also this last slide. So thank you for your attention.
Okay, thank you, Job, for this beautiful overview. We have time for questions, remarks. Okay, oh, yes.
Yeah, just one question. Between the Szemerédi result and the arose conjecture, what is the gap that is still missing? So I was not able to keep the...
Yeah, so let's see. The main problem to solve is to optimize the dependence of n on epsilon and k. Once you get, so once the behavior of n, so the minimal n for which this holds, as a function of n, once that's sufficiently small, one would prove Arose's conjecture. And people are...
Okay, so it's the large n of n that you need to control.
Yeah, so you want n to be as small as, you want this theorem to hold for an n that's as small as possible as a function of epsilon and k.
Can you put again the arose conjecture, please?
Yeah, yeah.
Okay, thank you. Other questions, remarks?
So you said that Grothendieck inequality allows to show the equivalence of uniformity and expansion for graphs that have a certain symmetry.
Yes.
So I was wondering, we know there are certain cases in which Grothendieck inequality doesn't hold, I mean extensions that do not have this constant. Could this be used to show families of graphs for which this equivalence does not hold?
I mean, so we know counterexamples to
Yes.
versions of Grothendieck. Oh, that's interesting. I never thought about that. So I told you there's some bad families of graphs, but the constructions of those graphs, they have nothing to do with counterexamples to versions of Grothendieck's or examples that give you lower bounds on the Grothendieck constant. They have nothing to do with that. So as far as I know, the counterexamples I know to Grothendieck's inequalities typically concern trilinear forms. So there's a sense in which Grothendieck's inequality concerns bilinear forms, matrices, and then the natural direction is try to extend this to trilinear forms, and there most of the time it fails. There's no absolute constant. But I don't know how to translate that back to graphs. Perhaps that could say something about three uniform hypergraphs, but that's a nice idea. I haven't thought about that.
Okay, thank you.
More questions, remarks? Well, I have one question. You started assuming that your graphs are simple. Is this very essential, or can you, I think these random graphs, can you also consider them with multi-graphs?
Yeah.
So there is nothing essential in this.
Yeah, that's not essential. The analysis, I think, becomes a little bit hairier, but that's not essential, no.
So these notions by Erdos, Renyi, random graphs can be extended to multi-graphs.
Yeah, directed graphs, multi-graphs, sure.
Right.
Yeah.
Okay. If no more questions, then let's say thank Job again. Thank you very much.
Thanks.
Be on the other side, so if you want to join.